Let us continue with the next session of this lesson. We have completed our walkabout around the Chemcad application window, and we are ready to start building a simulation model. Let us first introduce a problem that we are going to be building a simulation model for. Consider a vapor stream of ethanol and water that is to be condensed using cooling water. The stream contains 500 kg per hour of water and 500 kg per hour of ethanol. This means that you have 1000 kg per hour stream with composition of 50% by weight of each of ethanol and water. The temperature of the stream is 140 degrees Celsius and the pressure is 3.5 bar absolute. The stream is to be cooled down to 120 degrees Celsius in the cooler, after which the resulting liquid vapor mixture will be separated using a flash drum. The cooling water comes in at a temperature of 30 degrees Celsius in stream 5, and then it leaves at 40 degrees Celsius in stream 6, which means that you are only allowed 10 degree temperature increase in the cooling water system. Take a look at this flow sheet right here. This is what we are going to build in Chemcad, and then we will, once we have built this, we will specify the components, which are water and ethanol, and then we will continue to specify the stream such as the feed stream, which we know the composition, the temperature and the pressure and the flow rate, and then we specify the stream here. You know, the temperature of stream 2 is 120 degrees Celsius, and you know the temperature of stream 4 and stream 5. The first thing that we will need to do is to select our system of engineering units. Remember, that is in the format menu. As we have indicated, the preloaded default engineering units setting that Chemcad comes with is the English system. We will be using SI for most of our calculations, so I am going to select Common SI as our preferred set. The Common SI gives time in the unit hour, and the mass or mole quantity is given in kilogram. This, as you can see, already satisfies our flow specification, as our flow is given in kilogram per hour. The temperature is in degrees Celsius, which is the temperature units that we are using. So far, I think I am happy with the Common SI. If you want to save the Common SI as your default setting that will be loaded every single time Chemcad starts, you can click Save Default. But at this point, I'm not going to do that. Remember, at this point, you don't have to get everything correct right away, as you can always come back at any time during the model building, model simulation run, or even after the execution, to come and change or select whichever units that you would prefer to be used within Chemcad. Okay, we can now start to build the flow sheet. We will start by first introducing the feed to the process, as this is the way we can introduce mass into our system boundaries. We will be working from the all unit ops group tabs here. The feed unit op is right here. By moving the mouse over the icon, you see that it gets highlighted. As you can see, there's a black corner right here at the bottom right corner. If you click here, the pop-up window expands, showing you all types of feed arrows that you can select to use in your simulation. We will be using the first in the list, so you can click it to select it. If you move your mouse back onto the flowsheet workspace, you can see that the cursor is now represented by the selected unit op icon. You can right click on the mouse to deselect or unselect the unit op that you have selected. Alternatively, you can hit the escape button on your keyboard. Most of the shown unit ops icons are actually groups of different types of that particular unit op. For heat exchanger, the heat exchanger icon, if you click on the expansion arrow, is that of the first heat exchanger on the list, which is a simple cooler emblem. If you select a different heat exchanger, for example heat exchanger number 3, now the icon on the heat exchanger group changes to that heat exchanger 3. Or if you select that of kettle reboiler, as you can see now it becomes that of the kettle reboiler. You can show that with other different types of unit ops. For instance, if you look at distillation columns, the shown icon is that of the first one in the list. If for instance you select this one right here, the one that will be shown in that now becomes the last icon that we have selected in that group. The reason I'm explaining this is because of the fact that you can click once on the unit icon and select the unit op. The selected unit op on that time will be the one that is shown on that group of unit ops icon. As you can see on this, the selected one now becomes the kettle reboiler. If we go back and select this, if you click once on this, the selected icon now becomes that of a simple heater. Let's go back to building the flow sheet for our simulation project. We first need to introduce two feed streams, one for the process stream, that is the methanol and water vapor, and the other for the cooling water. We will just click once here on the feed stream to choose the type that is currently selected within the types of this particular unit op. As we bring the cursor onto the flowsheet window, you can see the selected type of unit op. You can click anywhere on the space to place the unit op at your desired place. We want to place the first one here and then the second one here. Note that if you continue clicking on the flowsheet window, the feed unit op will continue to be placed on the workspace. To deselect the unit op and go back to the mouse cursor, right click on the mouse or just hit the escape key on your keyboard. Let's just delete this because we do not need them. The next, we now need to bring the product streams. We click on the product to select the currently chosen type of arrow. We will need the product stream for the gas, the product stream for the liquid on the out of the flash drum, and the product stream for the cooling water. And then we right click to deselect. We can arrange this however way we need to arrange them, but we will do them at a later stage to just make our flow sheet neat and tidy, as you will see. We will now need a heat exchanger. The type that we need at this stage is just a simple one to exchange heat from the vapor into the cooling water, which requires 2 inlet streams and 2 outlet streams. If you expand the heat exchanger unit op group type, you will see that the heat exchanger that we need is either this or that. As you can see, this one has the inlet for the process and the outlet for the process, and then the inlet for the cooling water and the outlet for the cooling water, similar to these two. We will select this one. In Chemcad, the inlet is always indicated by a blue dot and the outlet is indicated by the red dot. We will select this and then we will place this heat exchanger around here. Remember to right click to deselect the heat exchanger. The next unit op that we need is the flash unit. If you click on the flash unit op group type, and expanding that, you see that you have a number of different types of flash separators. I'm just going to select the simple one here indicated by flash 1, and I will bring it I want to place it around here. Remember to right click to deselect the flash separator. Let us now use stream connectors to connect the unit ops and transfer the material flow across the flow sheet. The stream connector is right here. Note that once the stream connector is selected, the cursor becomes a small cross line, as you can see here. If you move the cursor over the unit op or the equipment, the inlet and outlet connections become activated as blue and red dots come to life. If you hover over the heat exchanger, you can see all inlet and outlet stream connectors. Here the inlet, here the inlet, here the outlet, here the outlet. And also if you move your cursor over the flash drum, the feed only has an outlet, and then the product only has an inlet. We will first connect the process feed to the heat exchanger. We click the feed unit outlet stream connection point. Notice that once the stream connector is connected, the hairline guides are activated to guide you on how to connect your streams. We will connect the stream to the heat exchanger inlet right here. Note that the stream ID number 1 is shown on the stream. Chemcad uses square boxes for stream IDs, and it uses circles for equipment or unit op IDs. We can move the heat exchanger to align the equipment and make the process stream straight. Remember to right click. Okay. Now let us connect the process stream from the heat exchanger to the flash drum. We will connect it on this outlet point. As you can see, again, you have your hairline guiding you on how to navigate around for the connections. As you hover over the flash drum, you can see that there are about 6 inlet streams. It does not really matter which stream you connect to, as they all get mixed inside the drum. So you have the leisure to select on your preferences. I will select somewhere close to the top, just randomly. As you can see, Chemcad connected to the second from the top, as it felt I was closest, is the one that I was pointing closest to. If you would prefer to connect the stream somewhere around the middle, you could do so by right clicking on the stream and then click and reroute stream, and then you can now select to connect at your preferred location. You can now realign the 2 unit ops to make the stream connection straight. I really prefer very neat flow sheets where the stream connectors are straight. Next, we can connect the gas outlet stream and the liquid outlet stream from the flash separator. This is where you can see the use of the hairline guides, how they help you to realign your connection. As you can see, for the liquid connections, there are 2 connections, the one somewhere right here and the one right at the bottom. I have used the one right at the bottom. The reason we have 2 liquid connections is that it becomes very helpful when you have 2 liquid phases in your system, where you can now connect the heavy liquid at the bottom and then the lighter liquid somewhere here in the middle. At this point, it does not really matter where you take the liquid, because there's only one liquid phase. We can bring this outlet stream for the heat exchanger cooling water down here, so that it becomes easy to connect. Okay, you can click on the heat exchanger to check the required specification in its current connection state. The dialog box that pops up tells us that you can use this simple heat exchanger model, and the heat exchanger can work in its current connection state. That is, it will work even without the cooling water streams connected. Looking here on the dialog box, this exchanger type only require the user to specify one of the following process or design specification for the exchanger to be completely specified. That is, if you specify the outlet temperature of stream 2, Chemcad can now calculate the required duty, the vapor fraction of stream 2, or subcooling of stream 2, or superheating of stream 2, depending on what the condition is. Or if you specify the heat duty, then Chemcad can calculate the resulting temperature of stream 2, the vapor fraction of stream 2, or the supercooling or superheating of stream 2. The other specification that you can do is the delta T between stream 1 and stream 2, which essentially is similar to specifying stream 2, because once you know the difference, you know the other. Just in passing, you can also specify the pressure drop, which will now help with the calculations of the friction losses or the pressure losses in this in the process, which at this point we will not be interested in. As you can see, I've clicked OK, and then Chemcad comes back and tells me that there is an error because the heat exchanger, the simple heat exchanger model, has no specification for that required one input case. We will not concern ourselves with that error because we are not going to use the heat exchanger in its simple heat exchanger mode. Next, we will have to connect the cooling water streams. I will use the connection guides as indicate the hairline connection guides, and then I will connect the outlet stream. Okay, if you go back to the heat exchanger, at the top of the dialog box you can see that the heat exchanger model is no longer a simple heat exchanger model, but now a proper heat exchanger as indicated by its name here. And also the required specifications have now changed. If you check here underneath the simulation mode, you can see that you now have a bit more options, indicating that this is a more detailed and complex heat exchanger model. If you click OK again, you have your errors and warnings telling you that your heat exchanger does not have any specification. If you have noticed that as we continue to connect the streams, Chemcad automatically numbered the streams 1, 2, 3, 4, 5, 6 sequentially as we were connecting them, which means that as we continue to connect the streams, Chemcad names them. If we had before we connected stream 3 here, which is the gas, had we connected the water line stream here to the heat exchanger, that would have been stream 3. So Chemcad automatically numbers the streams as you connect them. If say one stream we delete stream 2 and it becomes not necessary anymore in the flow sheet, and the next stream that we connect will become stream 2. So basically Chemcad also reuses the streams that you have deleted, the stream IDs for streams that you have deleted. If you have connected your streams differently from what I have done, and you would like to have the same stream IDs, you can do so by double clicking on the stream, so right clicking on the stream and then change stream ID. If for instance you wanted to name this to be stream 4, you can click OK, and then Chemcad tells you that stream ID is already in use, and then you can click OK so that it switches the stream ID 3 and 4. Now this will become stream ID 4, and then the stream ID that is stream ID 4 right now will become stream ID 3. Clicking OK to show you exactly what happened, but I don't want to do that, so I am going back to revert back to what we had, and then also it tells you that stream 3 already, so then it swaps them back. This is because of the fact that all stream ID, all streams, each stream needs to have a unique ID. You will not have streams with that are sharing an ID. That's why Chemcad clashes. It shows you that clash when you are trying to name to change the stream ID to an ID that is already. Our flow sheet is complete. The next step is the selection of the chemical components. Just a quick thought: we only have water and ethanol in our system. We have water and ethanol in the process streams, and we have water only in the cooling and utility system. To select the components, we can use one of the three ways. You can use the Chemcad Explorer. In the tree structure here, you have the select components, or you can use the shortcut on the shortcut menus, or you can come to the toolbar on the thermophysical menus. You can use the select components option here. Feel free to use any of those ways. In the select components dialog box on the left hand side here, we have a list of all available components in Chemcad, going all the way from number 1 to number 2277, which can be quite a struggle to find a specific component. To address that, you can use the search function here. Chemcad offers basic keyword search options. There is 4 of them, which means that the selected ones are the ones that it uses for searching. As you can see, the case number is not selected, and if you type anything in the search dialog box, it's only gonna search using ID, name, or formula. The first one, the component ID, which is the number here, it's not so easy to remember that hydrogen is number 1 and siloxane is ID number 2277, so it can be a bit of a problem or difficult one to use. The second search keyword option is the component name, which provides an easy way to search. The third one, the third keyword option is the formula, which is also an easy way to search. The last option here, the case number, is the chemical abstracts registry number, which is how the chemical species are registered in the CAS database, and also not a very easy one to know unless you deal with the chemical registry database and you know the numbers. Just to take you through the search option, the search functionality in Chemcad. If you type in ethanol, you will see that the first word that you see is methanol, which means that Chemcad searches within the word. It does not search the whole word, so it can search part of it. It uses whatever you search, it searches as it can be part of the word. And one little irritation for me also is that it still gives you the whole list of components, and then it just moves on around. So what you need to do is you need to click on next, and then the next one on that, as you can see, it becomes ethanol, which we can select and put onto the site. The next one is water, which the first option now becomes water, which we can add into the system. That is all for the component selection for our process. Just to give you a little bit more on the advanced search options, you have that where you can search based on a number of other criteria. If you click on OK, you will see that Chemcad automatically takes you to the thermodynamic method selection. So here you can select how the components interact. and then you can also give the range of temperature operations, the operating condition ranges, such as minimum temperature, minimum pressure, maximum pressure. We will leave this as they are for now, or you can change them, because we know that our temperature max goes above 100, so we can put in if we know it goes above 100, you can put in 200 for instance, or you can leave it as it is. If you click OK, Chemcad automatically recommends a thermodynamic property method that you can use. As you can see here, it says for the K it's going to use NRTL method, and then for the it's going to use the latent heat method for enthalpy calculations. These are suggestions that Chemcad gives you based on your system. You still need good judgment as a process engineer to know which thermodynamic model works with which system. In case you are working with heavy paraffins, heavy waxes, you should be able to advise Chemcad or to select the property method that is suitable for that. We will at this point just accept it, and then as you can see now, it takes us to the thermodynamic settings dialog box. The global K value model is the NRTL model. If you click in here, you can see a number of thermodynamic model that is used to calculate the K value. If NRTL is not your preferred model, say your preferred model is Uniquark or is say SRK, you can select that. At this point, we will just leave the model as NRTL. The enthalpy model, as we stated, is latent heat. If you have a better enthalpy model that you prefer for your system, you can also select that here. For this exercise, we will leave it as it is. And then also here, then you have the transport properties that you can select for your system. Here, Chemcad just alerts you that it has found some binary interaction parameters for the selected activity coefficient model. For NRTL, Chemcad will automatically look for binary interaction pairs. If it doesn't find any, it is likely to go back and select an equation of state type of model such as SRK. We have completed the drawing of our flow sheet, also completed the selection of chemical components. We have specified the thermodynamic calculation methods. Next, we need to provide feed stream specifications and also some design specifications for our unit operations. And our simulation model should be ready to run after we have done that. We will first start with the feed stream specifications. This can be done from the specification menus in the toolbar. Here, you have the feed streams. As you can see, Chemcad has identified that there are two feed streams, which are stream 1 and stream 2, because of their connection to the feed unit or op item. You can also specify the streams by double clicking them directly as follows, which then you can use this to specify the streams individually. The feed stream needs to be specified in full, and the cooling stream we will have we can only specify the inlet temperature, and then the flow will have to be calculated by the heat requirements from the heat exchanger, as you will see. Let us specify the feed stream, the process feed stream. We will double click on the process feed stream. What you see here is you can also give the stream a name if you like. Here we will name the stream as feed. Click enter. The temperature of the stream is given as 140 degrees Celsius. Click enter. And the pressure is given as 3.5 bar. Click enter. If you look here on the component unit, you have the units kilogram per hour. You can click on this, and then as you can see, it has a drop down menu which lists all the units that you can use to specify your component unit. let's leave it in kilogram per hour. If you leave it in the default kilogram per hour, then which means that you will have specify your component unit in kilogram per hour. And as you know, we have 500 kilogram per hour of ethanol, and then 500 kilogram per hour of water. As you can see, Chemcad automatically calculates the total molar flow for you, which is essentially the sum of all the components. Another alternative that we can look at is we can change the component unit to now weight fraction, and then what you can do is you can enter this as 0.5. But because of Chemcad knows that that's what this means, it has automatically calculated for you. If you click flash here, Chemcad does some evaluation and calculations. As you can see, the enthalpy of the stream has been calculated. Furthermore, Chemcad has evaluated the liquid vapor conditions of the provided stream at given conditions. As you can see that it gives you that the vapor fraction of the stream is 1, meaning that the stream is at a temperature equal or higher than the dew point, with a temperature higher than the dew point indicating that the stream is superheated. The vapor pressure of 0 will indicate that the liquid stream is at a temperature equal or lower than the bubble point, with a temperature lower than the bubble point indicating that the stream is supercooled. And we have been told in our problem statement that the stream is the vapor stream is superheated. To what degree of superheated we do not know, and we can evaluate that in Chemcad. If you clear the temperature here and enter the vapor fraction of 1, and then you click flash to perform flash calculations, Chemcad calculate the dew point temperature, which is 129 degrees Celsius, and which now tells us that at 140 the degree of superheating is about 11 degrees. If instead you put the vapor fraction of 0, indicating that the stream is at bubble point, you can do flash calculations, and Chemcad will find the bubble point temperature, which is calculated here as 117.9 degrees Celsius. However, we know that the stream is not at saturation, it is indeed superheated, and then we can enter the temperature. Okay, Chemcad tells us that we can only provide 2 specifications, so we have to clear the vapor fraction specification, so that it now allows us to provide the temperature specification, which we can now flash and get back to where we are. The next steps that we need to do are to first specify the cooling water requirements, and secondly, we need to specify some process design targets for our heat exchanger, and finally some specifications for the flash unit operation process targets. For the cooling water requirements, we know that the cooling water supply temperature is 30 degrees Celsius. We can further specify that the pressure of the cooling water to be whatever process pressure that you can feel, whatever pressure that you feel your design can handle. Let us start with the temperature here, which is 30 degrees Celsius. The pressure, for simplicity, will go with the pressure similar to the process pressure, which is 3.5 bar absolute. You can specify any pressure, 1 bar, 2 bar, or whatever pressure that you feel your cooling water system can supply and your equipment design can handle. Okay. What we know is that we need to cool the stream, the process stream, which is stream 1, down to 120 degrees Celsius. We do not know how much cooling water we need to achieve this. Just for experimenting, let us say that we will require 1,000 kilogram of water in the stream. We do not know how much cooling this cooling water will do. Will our process stream reach and pass the targeted 120 degrees Celsius? We do not know. We will see when we do the simulation. Let's flash this and we move on. Moving on to the heat exchanger, you can double click to open the design specification dialog box. Here you can see that the simulation mode is on number 0, which states that you enter the specifications and then run Chemcad simulation. If you click on to show the list of simulation modes available, you can see that you have shell and tube simulation for performing detailed shell and tube calculations, which we will spend more time later when we demonstrate heat exchanger design and specification. And then you also have shell and tube fouling factor, you have blade exchanger design, you have double pipe heat exchanger simulation. Down here you have the utility option, which states that it is currently turned off. The options that we have under the utility option are that we can use Chemcad to use the energy balance to calculate the flow of stream 5, as you can see here, which gives you the cooling water requirements, or we can calculate the flow of the process stream, which is stream 1. For now, let us leave the utility mode on off and demonstrate the trial and error calculations as we have planned. Chemcad also allows you to specify the pressure drop for each of the streams that flow through the heat exchanger. This will be helpful when you do the momentum balance for the piping and pipe sizing calculations. For now, we will leave this on default, which we are told that Chemcad will take a 0 value for each of the streams. On the specification tab here, we are told that we need to enter one specification only, and we have a number of options to select from. We can select to specify the temperature of stream 2 here, which we know that the process target is to cool down to 120 degrees Celsius. We can also opt to specify temperature of stream 6, which we know that we have utility limitations to only heat the cooling water to 40 degrees Celsius. We will opt to select the temperature of outlet temperature of the cooling water. Next, we move to design specifications for the flash unit up. You can see that we are by default on option 0, for which the vapor liquid separation is calculated on the basis of the inlet temperature and pressure. Other available options include us specifying the vapor liquid and pressure, and then Chemcad calculates the temperature and heat flow conditions of the incoming stream outlet, and a number of other options where we specify the temperature and pressure, and then Chemcad will do their calculations for the vapor liquid separation and the heat flow. Except for this one, most of these basically may require addition or removal of heat, which essentially means that the flash unit is not just a simple vapor liquid separation. It may also have additional heating or cooling requirements, which in actual application or equipment design, it will not be a single equipment, it will not be a single flash separator. It will be a heat exchanger, then a flash, or maybe a valve to flash or reduce the pressure, or a compressor in that case where you need to increase the pressure. But for this purpose of this calculation, as we have stated, we will just be flashing at the conditions of the inlet stream, and we will continue with the specification of flash mode 0. At this point, our basic flow sheet should be complete and ready to run. What is usually recommended here is that we run each unit up separately. This is to make us to be able to identify the exact origin of errors if there are any. So I will start with the heat exchanger. I right click and say run this unit up. The run started, it runs, and as you can see on the run trace window, it tells you that the run started and the run finished after not so much time. I think this is started and completed after 3 seconds. And then we move on to the second one, which is now the flash. We can also right click and say run this unit up. As you can see, it ran and completed within very little time. Now we can start looking at our streams. The first thing to look at will be what's the temperature of stream 2. We see that the temperature of stream 2 is 128, just around 129 degrees Celsius, 128.96. So which is still quite high, which is still higher than our target, our process target of 120. And then we can move to stream 3. We can see that most of our process of our water and ethanol is still in the vapor form. As you can see that 498 and 490 went to the vapor. And in the liquid flow is just around 10 kilogram per hour, as compared to almost 990 kilogram per hour in the vapor stream. So in that, now what we can do, what we can opt to do, is we can increase the cooling water flow rate to effect more cooling onto the process stream. Without wasting time, let's do that. We can increase the cooling water flow rate to 1500 kilogram per hour, and then we can run the simulation, and then we can look at and you can see again there's not much change in the temperature of stream 2. It's still 128.8. Go back to the cooling water flow rate, make it what value can you select? Let's select 3000. Okay, and then click run, and then look at the temperature of it's changing, but very, very slowly. So which means that you have to keep doing trial and error to get to the temperature that you are looking for to be able to. But if you look at to be able to achieve the process target, if we look at our process streams, we can see that slowly the flow of the process flow of the liquid is increasing. So what we need to do now is we now start becoming more wiser about how we are going with the calculation. This we can do in the heat exchanger calculation here by specifying starting to do the utility calculations. We will get to that in just a moment here. To do that, we use the utility option of the heat exchanger. What we now know we need to do is we want because the process stream, which is flow of stream 1, is given, it is the process flow that we have to achieve. We can select the option where we calculate the flow of stream 5. We click on that. Once we click on that, you can see that now here on the specification tab, we are required to specify 2 specifications for us to be able to calculate the temperature of stream 5. We know that the temperature of stream 6 still has to be 40 degrees, as this is a limitation. And now a process target that we know is we are targeting the process temperature of stream 2 to be 120 degrees Celsius, which we are okay with. Then we can accept that, and then we can run. And then now if you come in here, you will realize the temperature is at our design target, and then the flow of stream 5 has now been reevaluated. As you can see, now is 26,000 kilograms, which is 26 tons per hour. By the increments we were doing, we needed to keep incrementing quite a bit to get to that. And then if you look in here onto the outlet of our flash drum, you can see that the ethanol, the stream 3 is rich of ethanol, and it's comprises of about 1 part water, 2 parts ethanol, and then that of the liquid would be 4 parts water and 2 parts ethanol. So now we have rated or calculated our heat exchanger to meet our design specification. And now if you look at this now concludes our targets. This concludes our calculation targets, and we can be happy with our basic flow sheet that it does what we require it to do. Before we start looking at some of the reports that we can draw from our flow sheet, let us first save the simulation. What we have been basically flirting with danger in the situation, in a sense that we haven't been saving our simulation. Had the power went off due to load shedding, we would have lost this entire simulation, because Chemcad does not do autosave. So let us save this. We can use the shortcut save here, or you can use any of the menu options in the toolbar. You can use save, you can use save as. So I will go with using just save. And then what you can see is I usually like to save under Chemcad. Automatically, once installed, it creates inside my documents, it creates my simulations here, where you can save your simulation. So I will just save it here, which we call it Chemcad module 1 episode 2. No, it's just Chemcad module 1. Chemcad module 1, that's the only simulation that we did in module 1, so it's fine. I'll just leave it as that, and then you can click save. Okay, before we conclude today's lesson, let's just look at the sort of like reports that we can look at within Chemcad. The first thing that we can do is you can look at the stream compositions, which is in the report menu. You can select the streams that you want to look at, or you can look at all streams, or you can look at the fit streams, product streams, or unit streams. Let's just look at all streams, which now actually, when you look at this, it gives you the stream properties for all the streams, stream 1 to 6 of our process flow sheet. What it gives you, remember, we have only entered this the name for stream 1. If we had we entered the names for all the streams, we will see the names for those streams. Then it gives you the temperature, it gives you the pressure, enthalpy flow, mole fraction, vapor mole fraction. It gives you the total mole flow, mass flow, and also the individual component flow. One of the other tweaks that you can do here on Chemcad is say we want to change this heat exchanger for another heat exchanger. If you come and look at the heat exchanger tab, say we want to swap this heat exchanger for this one here, which if you look at it, it also has 2 inlets and 2 outlets, so which will definitely work in this situation, or this one or this one. So the easy way to do that, you just right click on this unit, and then you can click on swap this unit, and then this operation will clear and undo the history. Would you like to proceed? We say yes, and then we come in here, and then we swap it with the heat exchanger. Then you click on this, it automatically connects it for you. If you double click on the exchanger, you can see that the specifications remain the same, because essentially these heat exchangers, for say heat exchangers that have 2 inlets and 2 outlets, they work essentially the same. What you have different is sometimes it's just the icons that are different, but the calculations, the underlying model, mathematical model underneath, they're usually the same. So for this heat exchanger, the specifications, as you can see, it just swapped it. The specifications remain the same, nothing has changed, and then you can run your simulation, and it basically runs, and it converges, and it gives you exactly the same as you had before. Okay, thank you very much. This concludes today's lesson, and if you have any questions, I will be opening a blog on Blackboard for the discussion of this lesson, and then also you can send me an email, or you can come see me in my office. Thank you. Bye bye.